Hello everyone, let's get started for tonight. So we stepped into the new module of addition, subtraction and digital logic circuit. Before we go into that, let me discuss some more about this decoder and the component counting. And I think I did a mistake in component counting last time. Let me show you, and I'll explain some interesting features there, and we'll share with you. Just give me a minute. Okay, so you remember that we kind of started coming up with some generic formula like, okay, for an m by n line decoder, we need m inverter and m minus 1 into n and. That's true in that approach. I'll explain that in detail, this approach as well. But when I calculated it, I actually did say 3 multiplied by 4, but where it was like 3 by 8 line decoder, right? So it has to be 2 multiplied by 8, the 16 and to be calculated there. That means 16 NAND and 16 inverter to be there. So please make sure you adjust your calculation accordingly if you follow this formula. However, 12 and is a right answer too. Let me explain that. So here we are. So we have two choices to build the line decoder. Right. So let's start with this approach one, I would say. Okay, approach number one method, that we simply start with this inverter. Let's take example of 3 by 8. Right? So what we need 3 inverter, right, for these 3 input, like let's say I1, I2, I1 and I0, and then we need 8 AND gate to combine this output from inverter and the original one, all this outcome in a different form, right? So we probably will combine these 3 all inverter output to make a M0 output out of that, and then possibly we'll connect this and that one and this one to make M1, and so on and so forth till we reach M7. For M7, what we'll connect? We'll connect everything positive, right? Oops, not here. Non-inverted form. So that means in general, we can make it a generic statement that for M by N line decoder, we need M inverter and N M input and that essentially means N multiplied by M minus 1 to 2 input and. That is in general. 2 input and that's what we need in this approach. Now next approach number 2, . what we can do is a little bit different approach that will result in consuming less number of logic gates in the circuit. So that approach is based on how we start building up with a pre-built decoders. So we start with like let's say we start with 1/2 line decoder. So 1/2 line decoder is simple inverter. This is 1/2 line decoder. And then from there, if we want to build a 2/4 line decoder, then what we need to do, we bring another 1/2 line decoder, which is again the simple inverter. And then add 4 and they will be connected like, yeah, I can make the logic connection here like this. And then like this, like that, and like this. So this becomes your 2/4 line decoder. Now on top of this, we want to build, using this component, a 3/8 line decoder. What we can do, we can just bring in another 1/2 line decoder. And combine with 8 and then we start combining all these different combinations together with them. They will represent either one of the term. And so on and so forth. So we have like built a 3/8 line decoder. And using that, if we want to extend it to 4/16, 4/16 line decoder, what we need to do is bring up another inverter or 1/2 line decoder and combine with 16, like 1, 2, 3 till 16 different AND gate to combine them into a big 4/16 line decoder. So in general, you see that you have to have, in this case, like in general, M/N line decoder. You have to have M inverter, and then number of AND you need is basically N plus N/2 plus N/4 and so on and so forth, like that, till you get to 2. You get down to 4, this one, right? So for this case, 4/16, what you need is for 4/16 line decoder, you need 4 inverter, and then you need 16 plus 8 plus 4. That many AND gate. So this will be like 28 AND gate. So you see, like for 3/8 in that case, we need 3 inverter and we need 8 plus 4 equal to 12 AND gate in that case. So our calculation, final calculation was right in the previous problem. but it was not following our previous approach of calculating the number of input. And with this approach, you will always end up actually using more AND gate than this approach. Okay. And then we can actually do a generalize, like if you don't like this form, we can do another form, number of AND gates. So it is M inverter. And number of AND gate you can compute like this as a compact form, 2 to the power, okay, let me just take a little bit more space there, that many inverter, and number of AND is 2 of n 2 to the power I. So it's basically, let's put it, let's get it as an example, 4 by 6, now it works out. So for 4 by 16, so our number of AND gate formula in that approach is sigma I equals 2 log base 2 of n 2 to the power I. So for a 4 by 16, let's do that. So number of AND gate would become like 2 till log of 16 is 4, right? Is it? Log of n, right? 384, yeah. So it was like, yeah, 2 to the power I, which means it is 2 to the power 2 plus 2 to the power 3 plus 2 to the power 4, which is 4 plus 8 plus 16, which is 28. So you can think in that way also. Either way is either sigma formula if you want to remember, or it's basically you start with the highest number of AND you need at that stage and keep dividing them, adding them, dividing them till you reach 4. Question?
Professor?
Yes.
Are we expected to know both methods?
It's good to have, like you can apply this one, but if someone, some problem said you need to use like, use minimum number of possible gates, then you need to take this approach. And by the way, this is more practicable approach. We use like, this is more common approach in the digital logic area, digital design area, where we reuse any pre-built component and we extend on top of that. Okay.
Okay, thank you.
Okay. Now, back to our today's topic then. Any question on these, our topic of today, the addition subtraction? Let me check the discussion board if there is any. No, I don't see any there. Any question from anyone? So hopefully you realize after reviewing that lecture, the claim I always made from the very beginning of this semester, that computer doesn't know arithmetic. It doesn't know addition, subtraction, anything like that. All it knows is logical operation. And every arithmetic operation is actually mapped with some sort of equivalent logical operation. And then we get result out of it. And also, this simplified addition subtraction circuit, logic circuit is possible because we have the 2's complement format. If we haven't invented this 2's complement format, life would be much difficult to create a subtractor logic accordingly. Okay, so that's very important. To understand the implication of 2's complement and what that format means and how it is applied into your field of study. And another thing probably you have noticed that overflow detection. Overflow detection circuit is very simple. It is just one single XOR gate. But the theory behind it, why it works, it's a bit complicated, and we have one dedicated video for explaining that. So this is very important and very interesting concept of a very simplified circuit, why that XOR works for every case. In case of overflow detection with this kind of addition subtraction circuit. Okay, so if we don't have any question, then let's do a problem. Okay, let's do a problem. So we have started this ripple carry adder. The problem is this, like compute. So we have this 32-bit 32-bit ripple carry adder subtraction circuit with overflow detection. Okay, so and then if this has to be implemented with 1-bit 2-input NAND, how many NANDs are needed? Because it is again the basic logic gate counting problem. Here we are restricting ourselves to implement everything using NAND. Just to recall those, if you forget what this circuit looks like, just hold on, let me upload. Okay, so you probably recall this is the ripple carry adder subtraction circuit, and overflow or detection would be something like this. One XOR there. Okay, this is overflow. And then these are all full adder, 1-bit full adder circuit. And this is your full adder circuit looks like. So it composed of XOR and an OR. So in this problem, we all know how to convert them to the NAND. This is like 2 NAND, and this is probably 3 NAND. We'll come up with that. But what about XOR? XOR by straightforward, you can use 5 NAND gate, something like this. I'll show you. Like A XOR B is A bar B or AB bar by logic definition, right? And then it is like A bar B whole bar by De Morgan. If you apply the De Morgan on top of this, then it becomes this. So that means like we have to have one NAND for this inversion. So that means 2 NAND, and this whole thing is another NAND. So 4, and this overall thing is another NAND. This is 5. So 1, 2, 3, 4, 5. Right? So this way we can construct it. This is number 1, and this one would be number 2, B bar, and then this will be number 3, and this will be number 4, and then NAND, this will be number 5. Now we can make 4 input, 4 NAND XOR logic as well. So this is using 5. This one is using 5 NAND gate. Now with some logical manipulation and iteration, what we can do, we can actually come up with this logic basically. A, B, and then so this is your A XOR B. This is like a 4 NAND gate XOR. Now, how the derivation looks like? Derivation looks like something like this. It's A bar B, A B bar, that's an XOR. From there, we come to our previous arrangement, which is like A bar B whole bar, A B bar whole bar, whole bar. From there, okay, now this term and inside this term, right? So we can write something like this: 0 or A bar B whole bar, 0 or AB bar whole bar, right? We can expect 0 or something is that. 0 or A bar B is A bar B. Now from there, we can represent 0 by identity, with identity. We can represent 0 as this 0 as, let's say, B bar. Sorry, this is not a capital B. B bar plus A bar B, and these 0 we can represent as A bar, A B bar, whole bar. And then from there, we can write it equivalently. It's a B A bar or B bar whole bar, then A bar or B bar, whole bar, which we can rewrite using De Morgan applied individually as, let's see, A bar, sorry, this is the other term, right? This is like B bar or A bar or B bar whole bar. And then we can write it as A bar or A bar or B bar whole bar, and everything is brought together, and from there we can write it down, simplified it as B bar or A, yeah, by De Morgan, this one. This is AB and A bar or AB whole bar. Then further apply De Morgan on top of this. This is like B, AB whole bar, A, AB whole bar, whole bar. So here that ultimately finally that's what we are doing. This is AB whole bar, this is A, AB whole bar, this is B, AB whole bar, and then we are NANDing between them, which is basically A XOR B. Okay, so in this problem, let's use the XOR gate with the 4 NAND, this configuration, 4 NAND configuration. And let's calculate this with a 32-bit ripple carry adder subtraction with the overflow detection. How many NAND will be there? Let's do it in group. Let me open up the group, the rooms for everyone. I will move Karen to 6. Okay, and let's take maybe 15 minutes to solve this problem among ourselves. Let's open. Okay, so our times is up. Let's see what you have reached to. How about study group 6, Dominic Reed, James Chian, and Karin Tang? Did you guys come to a conclusion?
I got an answer, but I think it's wrong.
Okay, let's be confident. Okay, what's your answer?
I got 612.
Yeah, 612 is, why do you think it's wrong?
It was like I had trouble coming up with the combinations for like and or, I guess.
Okay, but I think 612 is the right answer. So do you want to share what did you do there?
So I just counted the number of NAND gates needed for like each component in a DC chain, like
Mm-hmm.
for the ripple adder, and
Mm-hmm.
then also like for like the XORs needed for each, I guess, from one of the numbers. It's like it's in a diagram,
Right, okay. Mm-hmm.
and then one last XOR gate for the overflow detector.
Right, exactly. Yeah, that's what you need to do. That's what you need to do. Okay, let me do it for others. Like I think you are right. Let me explain to other a little bit in detail. So let's go to the next page. Let me load uh, this thing. So we have this one as a full adder, and then inside each one bit full addition, is it that one? Yeah, we have internally this one. So let's do step by step, like Karen said, like we do step by step. And also remember to add this overflow detection circuit. Let's not forget about that one. That's your overflow. Now you see that half adder, HA, is one XOR plus one AND. So this means, as we just previously have seen, that one XOR is 4 NAND. So it is 4 NAND, and one AND is 2 NAND. Like one AND can be constructed with using 2 NAND. So it is 6 NANDs per half adder NANDs, right? And then the one bit full adder circuit. This is one bit half adder. This is one bit full adder, which is like one half adder, and one OR there. So OR is very simple, right? A or B by De Morgan is A bar, B bar, whole bar. So it calls for 3 NAND gate. One NAND gate for one inversion, second one for second, and the whole thing is another inversion. So 3 NAND is needed for that. So that means one bit full adder is 2 multiplied by number of NAND in half adder plus 3 NAND, which is like 2 multiplied by 6 plus 3 NANDs, which is 12, 15, right? 15 NANDs. Now, just for this part, that means for 32-bit adder, that the internal, this ripple carry adder circuit, we have these many, how many? 32, right? So we have 32 one bit full adder. That's basically, we're talking of 32 multiplied by 15 NANDs, which is 480 NANDs. Now we have 32 XOR, like here is the 4-bit circuit, right? For 32, to make it adder subtractor circuit, we need to add 32 XOR plus 1 for the overflow, total 33. So we have the 33 XOR in that case, which is like 33 multiplied by 4 nands, which is equals to 132 nands. Then total, we need 480 plus 132 nands, which is like 2. It's 6. Yeah, 612 nands. Okay, question? Is it clear to everybody? Okay, so we now know how that logical operation brings together addition, subtraction arithmetic, like for integers, integer addition, subtraction arithmetic. And this understanding you need for the project. So you should be able to complete your logical add and logical subtraction procedure in your project with this knowledge. So please go ahead and finish that part. Okay, then we'll move for the next step. It's multiplication. After that, the division. So we'll understand how that works and we'll implement accordingly into our project. Okay, the logical multiplication and logical division operation. Question? No? No question? Anyone? On any topic whatsoever?
Professor, could you go over the extract nth bit macro?
Extract m bit. Okay, that's a good point. Let me open that up. Okay, okay, try. Let's take 5-minute break, okay? Then 6:55 we'll be back with that, okay? Any other topic other than the extract m bit? No? Okay, let's take 5-minute break and we'll be back on 6:55, 6:56 about that. Okay, let's come back and address that that question. So I believe you wanted to know about this macro, right? Extract nth bit.
Yes, yeah.
Okay, so this one is something like this. Let's take an example with 8-bit, for example. Right? Let's say I have a 8-bit pattern, something like this. So this is your bit 0, 1, 2, 3, 4, 5, 6, 7. And our interest is to, let's say, extract this bit number 4. Bit number 4. So our usage would be something like that. Extract, let's say I have this pattern, which is, let's say this pattern is in your S1, okay? And then this number 4, so S1 has this pattern. Let's say T0 has this 4, and then we use this macro like this: extract nth bit with $T1, $S1, $T0. So our expectation would be in this case, after execution, after expansion and execution, that set of instruction, our T1 will contain 1 with this case, right? So that's the functionality. Is that so far so good?
Yeah, I understood that part.
Okay. Now question is, how do you implement it? It's we can mask it, or let me describe one simpler way to do it. It's basically, what you want to do is you want to left shift the bit pattern by T0 amount, and then, so let's say your T1 equals this, and then logical, like not logical, bitwise AND with 1. So essentially what we are trying to do, this operation, we left shift the whole pattern 4 times in this example. So after 4 times shift towards the left, what we get is 0, 0, 0, 0, 1, 0, 1, 1. So we are shifting towards left. So these 4 bit will go out of scope, and this guy will sit in the LSB side. And then we are ANDing this pattern bitwise. So ultimately we are looking at a result of 1. Make sense?
Yeah, that makes sense. Thank you, Professor.
Okay, all right. Anything else? Anyone? Okay, then if we don't have any other question, oh, by the way, I forgot to record that part. So whoever is trying to see the Zoom recording won't get this part. You might want to look at the YouTube recording, okay? Just to note. Anyway, I'm recording from now. But anyway, we are kind of done for tonight. If you don't have any other question, we have quiz coming up. It will open up tomorrow morning at 6 a.m. and due this Saturday by 11:59. Please make sure you turn it in within time. And review a multiplier for the next day. and complete your project addition adder subtractor, logical adder subtractor part. All right. Okay, we can stop now tonight. Go early little